the sake of it, I'll start with the building model stage. When we're approaching, we have some population of anything. In this case, it will be binary black hole mergers. The first thing we need is basically a model to describe what we expect to see. And once we have a model, we can start to understand the systematics associated with that model and build up our statistics. And then once we understand the statistics, we can develop the code to do the data analysis. And then we just have to wait for binary black holes to merge and be observed by LIGO and Virgo. And then once we have that, we can run our analysis and get our results, and then go back and write our papers, and then start tinkering again with our models and making sure we better understand the systematics, and continue that whole process over and over again. So we've now gone through this a couple of cycles, and we think that we're getting reasonably good at doing this. So I guess the first thing we need to know is how we characterize binary black holes. So this is just a diagram that was put together by a summer undergraduate research student I worked with last year, Jen, and it shows a schematic of a binary black hole system. These two sort of solid circles represent the two black holes, and they're labeled M1 and M2 for the masses of the two objects. I'll talk about the primary and secondary mass probably throughout the talk, and the primary is M1, and this is typically taken to be the more massive black hole. And in addition to mass, black holes have a spin, an angular momentum, which is a 3-vector. And so you can describe these astrophysical black holes in a binary by 4 parameters each, or 8 intrinsic parameters to the binary. This is neglecting eccentricity, which is very important, and there's good research on it, but it's not quite made it into our population analyses yet. In addition to these 8 intrinsic parameters, there are 7 extrinsic parameters which define the relative position and orientation of the merger throughout the universe. And of these, we've only really started doing population analyses on one of these parameters, which is the distance, where we're attempting to probe the distribution of redshifts of merging binary black hole systems. So now we understand a little bit about binary black holes. We can ask, what do we want to learn from these binaries? And I've broken this into roughly 2 categories. Because these black holes are so simple that they have no hair, they only contain mass and spin information, you can't extract a huge amount from the observations other than how those black holes came to be and how that binary came to be one that would merge. And so we're interested in the black hole formation, which we can use to probe the progenitors of these. We can ask, did this black hole form as a result of the collapse of a massive star? Did it form through the merger of other smaller black holes in what we call the hierarchical merger scenario? Or are they primordial black holes, which just formed from fluctuations in the very early universe? And from these, in particular, if we're looking at the results of stellar collapse, we can learn a lot about stellar physics by looking at the distribution of black holes. We can learn about how supernovae happen. We can learn about the different rates of mass loss, and potentially through that start to probe things like the metallicity distribution with redshift in the observed binaries. And then we can compare that to other electromagnetic probes of the stellar distribution and try to tie those things together. And on the other side is how the binary came to be one that would merge. And so we tend to talk about formation channels in this case. And by that we mean how we went from presumably some gas that collapses to form stars that eventually form black holes that go on to merge. And there are 2 main channels that we think about, although some more exist. The first main one is this isolated binary evolution, where here we have 2 stars that form in a binary and they co-evolve. And as they co-evolve, they'll interact. And so you might have tidal interactions, you might have mass transfer events between the different objects. And as the black holes explode, you might have some level of natal kicks to the black holes, which will change the properties of the binary. And the next kind of formation scenario is dynamical assembly in dense environments. So these are globular clusters and active galactic nuclei, where you have a relatively high rate of interactions between bodies. And so when you have close encounters between compact objects, they form binaries and harden and can eventually merge. And then there are other slightly more perhaps exotic scenarios like hierarchical triples, where instead of forming a binary stellar system, you have a triple system, and then you have some interesting three-body dynamics goes on in there. So these are just examples of the kind of formation of black holes and the binaries that we want to learn. So how do we learn this? As I said, we have to start by building models. And I've broken it down into basically three classes of models as I see it. They're what I've called the theoretical models, which, for example, are things like population synthesis or running n-body calculations of dense environments. And these have the advantage that once you've run your model, it's easy to extract the astrophysical information because your theoretical model tells you exactly what you're supposed to predict, what you're supposed to see, and then you compare that with what you've seen, and the one that fits the best, you say is the best model, and so is the best representation of reality. But the issue with that, and the big caveat, is you need really reliable theoretical models, and that's difficult to do. And so you're very sensitive to model systematics. So instead of that, you can go the completely opposite direction and go way over to the other side of these data-driven models, which is sometimes referred to as non-parametric. I don't particularly like that name, as often these have many, many implicit parameters, many more than any of the other models we might build. And these are the simplest versions of these are histograms and kernel density estimates. So you might take all of the masses that you've observed and just do a histogram, put them into bins. That's the simplest data-driven analysis you can do. And you're less sensitive to modeling systematics when you do this. But the disadvantages are you need lots and lots of data to make any kind of statements. And once you can make statements on sort of observational statements, it's hard to tie those back into the theory side if you don't also have the theoretical predictions to compare them to. And in the middle ground, where I'm going to stay for the rest of this talk, are these kind of phenomenological distributions, which basically means we take what we think we know from theoretical predictions and current observations, and what we think are our current uncertainties on those, and we just build toy models. And we can use these toy models to identify qualitative features, for example, whether there are bumps in the mass distribution of binary black holes. And then as we get more data, we can extend these models to include increasingly more physics, and then we can try to tie some of these qualitative features into the detailed theoretical predictions. So I have a couple of examples of these. The first example is a mass distribution model that I introduced during my PhD with Eric Thrain, which has since become known as the power law plus peak model in some of the literature. And for this, we were really targeting supernova physics and how supernova physics is going to influence the mass distribution of merging black holes. And so we were looking primarily at the two ends of the distribution, because there were various predictions from observed galactic black holes. There seems to be a mass gap between neutron stars and black holes at the low mass end. And then there's this theoretical prediction of pair instability supernovae, which say that there should be another mass gap above, say, about 40 solar masses. And you can see in this schematic illustration that we have those two mass gaps built into the model. And in addition to that, close to the edges of the mass distribution, we have these extra tunable parameters like a turn-on length, which may be influenced by the supernova mechanism for these lower mass black holes forming. And then at high mass, the exact position that the turn-off happens is going to be determined by mass loss efficiency, which then can be tied into things like metallicity of the stars previously. And the peak in this power law plus peak is what we've called here the PPSN graveyard. So PPSN is pulsational pair instability supernovae. And this is essentially when you have very massive stars, towards the end of their life, they become unstable to electron-positron pair production. And this can cause the star to contract very rapidly. And if you have a sufficiently massive star, then it's entirely unstable to this pair production, and the entire star is disrupted and you get no black hole, which is why there's a mass gap. But then if the star is slightly less massive, what you see is a series of contractions and then mass loss episodes, which look like pulses that you're emitting in a pulsing way, large amounts of mass. And what this can lead to is a kind of characteristic mass for black holes that formed through pulsational pair instability supernovae, or at least that was what we were hoping would come out of this model. And so that's what goes into our PPSN graveyard. And so in total, this is, I think, an 8-parameter model. And so with 8 parameters, we can really start hopefully saying things about those parameters once we have on the order of tens of events.
Colm, 5 minutes.
Thanks. So the next thing, the previous mass distribution was aimed at learning how the black holes are forming. And then we want to use the distribution of spin orientations in order to probe the formation channel, really. And so, as I mentioned, we have these dynamical capture events. And when that's happening, you have your black holes already formed and their spin vectors their spins are already existing, and they meet, and you don't expect any correlation between the orbital angular momentum and the angular momentum of the individual black holes. And this gives us this isotropic distribution, this flat line. So this flat line represents all of the dynamically formed binaries. Whereas if you have isolated stellar binary evolution, then there are all of the tidal effects and mass transfer effects that go on during the evolution, which lead you to mostly expect the spins to be aligned with the orbital angular momentum. Although if you have some supernova kick, some asymmetry in the supernova explosion, that can impart a linear momentum on the remnant black hole, which leads the spins to appear misaligned with the orbital angular momentum. And so if you have very large supernova kicks, you might find that even though you prefer the binary spin, the black hole spins to be aligned with the angular momentum, there may be some degree of misalignment. So here we have a two-parameter model, which says what fraction of the binaries form dynamically, and what of those that formed through isolated binary evolution, what was the typical kick strength? Or we have proxies for those two things, which are these sigma, and there's another parameter determining the fraction in each path. And the last thing is another test of formation pathways, which is looking for hierarchical mergers. So if you have two black holes that merge, the result is a third black hole, which has a mass approximately equal to the sum of the two black holes that formed. And so when we want to add in the possibility that in dense environments, these merger remnant black holes go on to merge again, then we just take the mass distribution of the first generation black holes and we multiply them by 2. And we say that's going to be the distribution of the second generation black holes. It's a toy model, but it's good enough while we have the amount of data we currently have. And there are other characteristics of these systems. We would expect that the second generation black holes typically have dimensionless spins about 0.7 times the Kerr limit. And this is a fairly generic prediction that varies to some extent with the spins of the initial black holes and the mass ratio of the binary, but not particularly strongly. And so this was a model that we introduced with collaborators at Northwestern University, led by Chase Kimball, for how to look for these hierarchical mergers and then whether we've seen them already. So for the sake of time, I'm going to kind of skip over this systematic slide, but the big takeaway is if we can have redundant analyses, then we can beat down our systematics. So multiple independent models and methods for analyzing the data. I'm happy to talk about this later or offline if people are interested. And then once we have those things, we develop our code. Kath mentioned Bilby, which was a code that we developed mostly at Monash during my PhD, and with many others, and is now spread to be a kind of global effort. And then on top of Bilby, I developed GW population, which was specifically targeting this kind of phenomenological population inference, and with various bits of GPU acceleration, which have really helped us keep up with the growing volume of data. And if you're interested in using any of these codes, feel free to reach out. I've added some links in here for people to check it out. So we have our models, we understand our systematics, we've written our code. Now we just need some data. So this is the data we have. This is as of the end of the first half of the third observing run of Advanced LIGO and Virgo. We had observed roughly 45 binary black hole systems and a few systems containing neutron stars. So we turn to the analysis of these, and there will be a more detailed talk by Shanneke Galaudegui tomorrow about what we learned in the collaboration analysis of this. And I've just shown some plots here. So if you think these look super exciting, you should make sure to definitely go to Shanneke's talk. But I'm just going to briefly mention, again, the results of this hierarchical merger analysis. And so here we were trying to ask the question, well, we've started to see some quite high mass systems. For example, in particular, this GW 190521 has a primary mass of about 80 solar masses, which is way higher than you would expect if pair instability supernovae behave in the way we think. And so that can be kind of a smoking gun that we're seeing hierarchical mergers. And so here I've I'm showing the log 10 of the odds comparing 1g plus 2g and 1g plus 1g, and then 2g plus 2g and 1g plus 1g mergers. So this is basically the joint probability that there is a second generation black hole. And the main 20-second takeaway is that for some of these events, particularly GW 190521, if we have a cluster mass that is sufficiently heavy to retain the previous merger that formed it, then it's very likely that this system was a hierarchically merged binary, according to our current understanding. And there are others which are strong candidates for containing just one second generation black hole. So in summary, in the past 5 years, we've observed about 50 binary black hole mergers, and that's allowed us to start identifying some qualitative features in the mass and spin distribution of merging black holes. And in particular, we've got suggestions of pair instability supernovae and hierarchical mergers. So in the last 20 seconds, I'll just ask the question, what next? We're currently analyzing the results of the second half of the third observing run, which had tens of additional open alerts, which suggests that there'll be tens of additional more events in there. And then O4 is scheduled to start in 2022, when we're really going to start moving into a data-driven era of population inference with binary black holes, and we can really start to test these models and make strong astrophysical conclusions. So thanks for listening. I'd love to take any questions.
Thank you very much, Colm. Okay, so we have a few questions online. So the first one is from Mike Creel. Is the Mmax transition always such a steep decline, or does it vary wildly?
Yeah, that's a really good question. So this is one of the things that we want to work out. And so in the paper that I've linked here, this collaboration paper, we considered a range of different mass distribution models. And the differences between those have some impact on how sharply the mass turns off at high masses. The short answer is we don't really know yet, but it's something we want to figure out.
So Kat Ross asks, is the M1 mass more influential in your models than the M2 mass? Is that why you focus on a mass distribution for it rather than the second black hole?
Yeah, another good question. So for this model, when we put it together, we decided to parameterize the primary mass and the mass ratio of the binary. And I kind of elided over that for time. But the mass ratio distribution of the binary can have some really interesting information in it. Whether you primarily see merging objects having close to equal masses or very unequal masses can tell you a lot about the environment in which they formed. It looks currently like we have a nice mix of the two.
So Fee Panther asked a question about Bilby. Any plans to incorporate consistency checking to Bilby, like posterior predictive checks, or does it have this functionality and I haven't noticed it?
Yeah, so with Bilby, we don't have natively posterior predictive checks built in, but with the population software GW population I mentioned for these population analyses, we do have that posterior predictive checking built in. And it's something that we're software development is an ongoing effort, and it's something that we want to make sure to have to make sure that all our inferences are robust to as best as we can tell.
Thank you. So Jonah Gannon asks about your hierarchical merging model. Since you seem to ignore the energy emitted in gravitational waves, which Matthew Bale's talk suggested was of order 10% of the mass of the product black hole. Does this affect your results?
It will eventually. But I think that the uncertainties we have currently, the statistical uncertainties are still bigger than a 10% systematic. But as we start to gather hundreds of events, then yeah, absolutely, we need to refine our phenomenological model and make it better and take into account that energy loss. Another thing that is kind of ignored in that model is you don't really expect the transfer function to just be multiplying by 2. There'll be some effect of the mass ratio distribution, which is shown here, that will go into it as well.
Okay, thank you. And the final question is from Ron Eakers. In your intro, you used a circle and, like most theorists, jump in at the model building. But history shows us that when new phenomena are discovered, e.g. gravitational wave detection, it's more frequently a serendipitous discovery of a new class of object. I think the predicted waveforms were spot on, but not the mass distribution. So why not start at the observations and see what new we learn?
Yeah, that's a great point. And that is, yeah, I guess when you're drawing a circle, it has to be somewhat arbitrary. And I don't know, maybe next time I give the talk, I'll start acquiring data.
That's an excellent answer. Okay, thank you very much for your talk, Colm. Can everyone join me in congratulating Colm again on the high surprise? Excellent, thank you very much. Okay, so we are going to move on to the next talk, which is the Anne Green Prize. This has been awarded now for about 5 years, and it's awarded for a significant advance or accomplishment by a mid-career scientist. It comes with the award of a medal, which was going to be awarded in person to the recipient in Sydney, but unfortunately that will have to wait for another time, and $2,500. This year, again, the Anne Green Prize was extremely competitive. And so it's with great pleasure that I can announce that this year's recipient is Keith Bannister from CSIRO Space and Astronomy. And he was awarded for pioneering work on fast radio bursts, its high impact in terms of the success of ASCAP and the successful implementation of the ASCAP FRB search mode, and for opening key new areas having high impact in high energy physics, galaxy evolution, the IGM, and cosmology. So please join me in congratulating Keith Bannister. And so Keith, if you'd like to share your slides, and you can start when you're ready.
You can hear me, can you?
Can hear you, thank you.
Okay, and you can see the proper view?
Yep, that looks perfect.
Okay.
You can start when you're ready.
Thanks, Kath. Well, thanks. It's a really great honour to get this from Kath. I'm very sad I couldn't be in person. We're in lockdown in Sydney. So, you know, like I'm looking forward to life returning to normal. I don't need to cross an ocean. I just want to go down the street. That would be good enough for me. Anyway, and also I hope Anne's online. But anyway, I was also looking forward to seeing Anne in Sydney, but I didn't manage to see her either. So anyway, hi Anne. I hope you're well. So yeah, look, it's really great to get this award. I work at the CSIRO. We're also called Space and Astronomy, and we're also called the Australia Telescope National Facility. The ATNF one tends to stick, so I'll probably stick with that from now on. So look, it's also funny getting an award like this because, you know, really it's the product of such a huge team effort. And I wanted to write lots of people's names down, and then it just took so long because, you know, I realized we've got 58 contributors from 25 institutes in 9 countries around the world. And, you know, it's a huge team effort, especially from some students and postdocs, you know, different levels of postdocs and also the staff. And, you know, they've done some fantastic hard work. So, you know who you are, and, you know, I'll pat on the back to all of you guys. I think you've done some fantastic work. You know, we've used a huge range of facilities too, and I have to thank all the TACs who thought it's worthwhile supporting us, and you know, for all these you know, facilities. And just at this conference, even there's been a few student posters, so I can encourage you to check them out. Danica Scott, Freya North Hickey, and Lachlan Marlock have done some. Clancy James and Matthew talked yesterday, and also Shilai Jang and Adam Batten gave some more talks on FRBs. I also am in debt to these two guys. I'm the guy in the middle. Ryan Shannon is on the left there, and JP McCart, or the late JP McCart, is on the right. JP is giving a somewhat smaller smile there, but usually had a massive grin on his face, especially when he thought he was, you know, being controversial, which he was quite often. And I dearly miss him. One of the key results of this whole work was the discovery, the discovery of 2.5% of the universe, and he made that, and he died, and he published that last year and died shortly after, and it was just a total tragedy. So I really miss the guy. Anyway, but he used to, just to start the idea of FRBs, he used to describe FRBs as the modern astrophysical whodunit. And he had such a way with words, and I couldn't agree with him more. It really was a total mystery. And I think one of the things that was really interesting hearing Colm talk as well, and the talks yesterday, is, you know, 5 years ago, when we were talking about FRBs, you know, it was kind of a pipe dream. Like, you just didn't think it was real. And, you know, gravitational waves, the same sort of thing. It was kind of, it seemed a long way or impossible or kind of a dream. And now it's kind of a thing. So, you know, that's really delightful. So fast radio bursts, you've probably seen this before. They're kind of millisecond duration bursts of radio waves. I've actually first met them when I was at my first group meeting in the very beginning of my PhD in 2007. So I walked into this group meeting and people are talking about 30 Jansky bursts, and I didn't even know what a Jansky was. Anne Green, funnily enough, was at University of Sydney at the time. She was working down the corridor, so that touched on something there. But it was kind of at the time it was totally it was kind of a mystery. We didn't even think they were real. So, since then there are about 200. In fact, this is not entirely true now. I need to update this slide. There's about 1,000 even published. So it's actually changed hugely in the last couple of weeks with a telescope called CHIME releasing some of their data. Until recently, they were difficult to find. Again, CHIME has changed all that. Most FRBs are very poorly localized, so we don't really know which galaxy they came from. For a long time, there was very intense and still is intense speculation about what forms these things. That's started to still massive questions there. Some fast radio bursts repeat, some of them don't. Or the first one ever known to be repeat lives inside a radio nebula, and that's not seen for almost all of the other ones. And they come from a huge range of galaxies, so there's not really an obvious progenitor, class that they point to. But yeah, so that sort of historical thing, I'm going to be a bit, now that I'm getting old, I can be a bit historical. I'm getting older thanks to COVID lockdowns, I can tell you that. Until about 5 years ago, many people didn't even think that these things were real. If you did, you were kind of hoping against hope, and people thought you were a little bit crazy. Distinguished Caltech professors, who will remain nameless, Shri, wrote essays and published the book, even took bets, and they were eventually lost. And I saw people hand out, hundreds of US dollars to various places at conferences, settling these bets. Distinguished Harvard professors claimed that they were aliens. But now we have, clever students and postdocs giving up and standing up and giving really interesting studies of these things, and it's a thing, and it's we have whole conferences about them, and it's just amazing how quickly it's all changed. And this is, thanks to the work of lots of people around the world doing lots of, impressive work. But I imagine gravitational waves probably feel the same, and gamma ray bursts felt the same at the time. So it's kind of, it's amazing how quickly things change. Why are they interesting? I'm interested in them for, there's two reasons really. One is, the rich phenomenology, structures in time, dynamic spectra, repetition, the energy densities involved. So you can cook popcorn on Neptune with an FRB if one happened at the location of the sun. So you could stand there with your glasses on, with your unpopped popcorn ready to watch the thing, and a millisecond later the movie ends, but at least you've got your popcorn cooked. We don't really know what makes them, what sort of progenitor. We've got a few clues from a galactic FRB that happened, came from Magnetar. The mission mechanism is like a total mystery. So that's kind of the progenitor question, but I think they're really interesting for another reason, and that's called propagation. So, as the radio waves propagate through the universe, they interact with the material along the line of sight, and that gives you some really interesting integrated quantities that you can measure, and then you can use to back out and work out what the universe is made of. There's kind of three broad classes here. You can talk about dispersion measure, which is the total ionized material along the line of sight. And that gives you the amount of stuff in the galaxy. The rotation measure, which is the electron-weighted magnetic field, and that tells you about how much magnetic fields there are, the magnetic field along the line of sight, and also temporal broadening of the burst, which you can see on the right. So a fast arrive exponential tail is typical for that. And that tells you about the density fluctuations along the line of sight. And I think that's kind of cool because especially the top one, the dispersion measure and the temporal broadening, you can't really measure them using any other technique other than having an impulsive radio wave. So that's kind of a useful thing that FRBs can do, you can't do any other way. So my title was a little bit weird, FRBs with ASCAP. So I'll tell you about what ASCAP at least is from my perspective. ASCAP is what happens when you take some high-tech goodness brought to you by the inventors of fast Wi-Fi. So that's the guy in the middle. There's a guy called John O'Sullivan. He was on the Wi-Fi patent. You build a telescope around it. So you start with with a good idea. You build a telescope around it. Here it is. When I described this telescope to someone at GIZMODO, they described me as an Australian scientist who was a massive nerd. you know, just be careful who you talk to, I suppose. I thought that was a compliment. My family called me a massive nerd. In this machine, there's 21,000 lasers, and it produces 200 terabytes a day, has enough optical fiber to get you from Sydney to San Francisco, and enough photovoltaics for a small town, which I think is kind of interesting as far as sustainability goes, which I'm looking forward to that talk after mine. So ASCAP, it's a big telescope, a big radio telescope, 36 dishes, 12 meters each, lots of high-tech stuff, and really huge scale. The bit that we use to find a fast radio burst looks a bit like this. So you have an antenna, it takes the data, it does a coarse filter bank, so it produces frequency channels, and then it splits into 3 in this thing called a beamformer. The top part goes off to the correlator, and that's what people use to do standard imaging that you might see in other talks during this conference. And then there's 2 branches of this that we use for fast radio burst detection. One is the square and accumulate part. So that's the search stream. So we use that to find the FRBs. And then we also have a voltage ring buffer that we use that to actually localize the FRBs. So once you find one, you have to reach back into the hardware and say, please stop. I need to look at the last 3 seconds worth of data. So we think of that like a live action replay. And then we can get exquisite, slow motion video, if you like, of your FRB arriving at the telescope. So that's that bottom part there. What I think is really funny historical note is this mode was implemented by a digital engineer at the ATNF called Andrew Brown. And the ATNF management at the time had told the craft collaboration that this implementation was too difficult to do, and it was delayed, and we should go away. I wasn't part of craft at the time. Which I think is interesting about this is I read a book about a guy called David Packard. If you've heard of Hewlett-Packard, it's the P in Packard. And he once gave an engineer a medal for extraordinary defiance above and beyond the normal call of engineering duty. And I like that because I like how, in engineering duty, you have to be defiant, and there's a normal call of engineering duty, but you should also give a nod to someone who is more, extraordinarily defiant. Anyway, so take a bow, Andrew. I think without you, this wouldn't have happened. So just a few science highlights. When we started with FRBs with ASCAP, we didn't have, they were busy commissioning the correlator. And so that was kind of, but they had antennas that worked, but no correlator that was working a lot at the time. So we thought we could take our antennas and we didn't need to point them in the same direction. We didn't need a correlator. We could point them in lots of different directions. And so that was what we did. So you can see in the photo in the bottom right, there's all these antennas pointing in different directions. And we pointed them, and we did a survey for FRBs, and it was delightful fun. So Ryan and I started out with this, doing this together. And within the first 2 days, we'd found one, and we knew we were in something. I was actually, when I first found it, the first one, I was sitting in my, next to my kids. They were watching a movie in the afternoon or something, and I was tapping away on the laptop. And up to this point, they'd been saying, Dad, have you got an FRB? And I'd be like, no. And they'd be saying, oh, it's okay, Daddy, maybe tomorrow. And then anyway, I finally found this FRB, and I'm like, kids, look, and it was pictured like what you see here, dynamic spectrum. And they're like, Dad, we're watching a movie. So not so interesting for them, but I think it was fun for me. It was more fun than the movie anyway. So yeah, we found these 20 or so FRBs. And Ryan did a really nice piece of analysis that you can see here, where we compared the dispersion measures and the fluences of these bursts with the dispersion measures and fluences of the Parkes bursts. And so Parkes is a more sensitive telescope, so it can measure more fainter bursts. And what he found was that the larger dispersion measures are all, bursts that have larger dispersion measures are also fainter in comparison with the brighter ones. And so obviously the hidden variable there is distance. So that was the first hint that these things really were cosmological, or a very good conclusive hint rather, that these things were cosmological. But the cool fun thing was using ASCAP to find a home for these FRBs, and that was kind of a lot of work. So basically we used that live action replay. The funny story about that was that we'd asked for the ATNF management to have like 2 special weeks just for us so we could look for FRBs. That 2 weeks had finished and we hadn't found anything. I went to the ops meeting and they said, oh, we've got to hand over the telescope now. And they said, well, the first thing we need to do is fix the, do a software upgrade. But Tony, who's sick at the moment, who's doing the software upgrade, he's going to be back tomorrow. So why don't you just have the telescope for an extra day? And of course, that extra day, that night, we've actually found the FRB we were looking for, the first one. And, you know, and well, the rest is history. So anyway, if you have a sick software guy, don't complain. So the first localization was this burst FRB 180924. Nice, a nice position you're in is sometimes, you know, the first thing you detect has a signal to noise of 200. That was fun. And we got a localization, a good position, and then a redshift. And, you know, it was really nice to basically detect a burst and, you know, you have its position, and yes, it's coming from a galaxy far, far away. That was kind of fun. One of the nice things, this is one of the highlights of my career to this point, was I wrote a piece with my postdoc Shivani and Shivani Bandari, and for the conversation, and this lovely Year 4 student sent her, did a project about Shivani, and you can see the poster here she did, and I just think this is the best thing ever because I couldn't have explained it better myself. So good on your Colette, Crisp. I hope you become an astronomer. I really like there's a piano in the background there too. That's kind of a good start. Anyway, so there's all sorts of things. Once you can localize FRBs, you can do all sorts of fun things, and I'll just give you a hot taste of them. One of the other FRBs we detected was this one, 1811-12, and that was an FRB. You can see that there's the galaxy in the middle, and the localization ellipse there is the FRB and the galaxy it came from. But off to the up left is another galaxy that's actually in the foreground, and so the FRB must have gone through the halo of that galaxy before it arrived to Earth. And so if you look at the FRB, and the FRB's, you know, traveled through that halo, and so that tells you something about, you can use that to infer the properties of the halo. And what we found was that the electron density was a bit lower than you'd expect, and you know, there was not a lot of magnetic field in there, and the low filling factor. So, you know, the idea was that halos are less dense and magnetized than you might have expected, or at least it was in this case. I just like this idea of...
Sorry, 5 minutes.
Okay, thanks. So once you start to find a few of these, you can look at different host galaxy types. And what we were finding was that, you know, if you look at double neutron star mergers or white dwarfs or quark-collapse supernovae, you know, you can draw what type of galaxies they come from, little boxes in different colors. And what you find is that FRBs don't really fall in any of those boxes regularly. So we don't really know exactly what types of things, you know, can produce FRBs. This is great work by Shivani. And this has been done a little bit more extensively by Heinz et al., which is another collaborator. It was really nice to see. I actually did astronomy because I wanted to take pretty pictures of the sky, and this is the first time I've ever been on an HST proposal that worked. So that was nice, and this is almost association with a spiral arm of a galaxy. It's really nice to look at this live action replay is really nice because this is a normal looking FRB, doesn't really look any different from anything else. But if you zoom in on the kind of microsecond timescales, you see all sorts of great stuff. This is a piece of work done by Hiran Cho, a very clever student, looking at you know, like microsecond resolution. And what you find is you know, the intrinsic pulse width here is, you know, of order 15 microseconds, or rise time of 15 microseconds, which is kind of incredible that this thing can travel halfway across the universe and still preserve time structure on that order. You know, you end up with 10 to the 22 joules per cubic meter, which is, it's a lot of joules. And yeah, some wonderful stuff. And you know, and when you look at the polarization over these few microseconds, you can see that it wanders around on the Poincare sphere, and that tells you that something very unusual is happening inside the ionized material that immediately surrounds the FRB. So that's kind of a cool piece of science. Not exactly sure what it means yet, but it's really cool. Oh, Shivani found this FRB. It was interesting that we, you know, it actually appeared as an image plane transient. So on the left is the image transient here that kind of appeared and disappeared. But really the thing I'm kind of most proud of was the work that JP did, which was, you know, finding 2.5% of the universe. And we've already talked about this, so I won't talk too much about it. But the idea is you've got, you know, roughly 2.5% of the universe is atoms that we can see, but we think that there was another, say, 2% of atoms that we can't see, and we wanted to find where those were. We think that they're, ignore my quotes. We think that they're in the intergalactic medium, and FRBs are this probe of that. So if you find an FRB, you can find its galaxy that it comes from, and then you can get a spectrum for that galaxy, and that gives you the redshift. If you can find a handful of these things, you can put them on a plot where you plot redshift versus dispersion measure, which is the Mokar relation, and the gradient of that line tells you about the density of the universe. And do a huge amount of work, and you get a plot like this, which I won't bother to explain all of it. Needless to say, you get a not quite so precise measurement of the omega baryon as you get from, say, Planck, which is the on the top right panel, the kind of the vertical shaded orange section, but nonetheless it agrees with Planck, and that's kind of a good step. So we hope to do that a bit more in the future with an upgrade that I'm currently working on. And this is what we call CRACO, or the craft coherent upgrade. You can also call it as, localizing an FRB a day by shoving 2 million YouTube viewers into a fridge. I'll explain that maybe another time. Needless to say, it's a lot of work, but we're getting close to doing it, and it's going to be good. I talk about this a lot, and so my daughter, who listens to me talk on the phone, wrote a poem about FIFOs, which I'll leave you with, and I'll take questions. Thank you.
Excellent. Thank you, Keith, for a really excellent talk. And I note that there is just a message in the chat from Anne Green saying, congratulations, Keith. You've carried out some amazing and innovative research. Every good wish for your future career success. So thank you, Anne, for that. That's excellent. Okay, so we have a couple of questions in the chat. So Reinhold Wilcox asks, what factors influence the localization of an FRB? Is it related to the number of currently pointing telescopes, like with gravitational waves? And when SKA is live, will most or all of them be localizable?
Yes, the short answer to your question is yes. If you want to localize in 2 dimensions, you want to have 3 antennas. In practice, you want to have as many as you can get. Usually in the ASCAP's case, we have upwards of 20 antennas all pointing in the same direction now. And when a FRB goes off, we use all of them that we can. Occasionally there's a technical glitch where we don't get all the antennas, but basically that's the key thing. With ASCAP, other telescopes will never be able to do good localizations. So typically single dishes or things like CHIME, which have a relatively, the key question is the longest baseline or the largest, dimension of the antenna. And if that's not about 1 kilometer or 2, at, around a gigahertz, then it's really not going to get you a good position. So, people are frantically trying to build, outriggers for telescopes like CHIME, and there's a telescope that's coming online in California that's going to do localizations as well. So, it's still a hot topic, lots of people building things.
Okay, Balu asks, is there a difference between the polarization for repeating and non-repeating FRBs?
Oh, look, that's a really good question. I wish I'd had time to, delve into the details of this stuff. And the short answer is there might be, but I don't know what it is. And other people who are more familiar with the literature might know. That's something that, there certainly is. What I can say that's different about, I'm not sure about the polarization actually. I think the polarization is so weird for everything. I'm not sure if there's a really good pattern. Certainly the pulse profiles or the dynamic spectra of repeaters seem to be different to once off. So the repeaters tend to be wider, and often they have sort of structure in the dynamic spectrum that points to them looking like, that sort of collects them in one particular part of that parameter space. But the once off ones tend not to have that structure.
Okay, so possibly a follow-up question from Lucy Strang. Are there any obvious subclasses of FRBs beyond repeating and non-repeating?
No, nothing obvious, I would say. I don't think, I mean, I guess there's always this on the one hand, there's a tension to try and unify everything to make sure for everyone to feel like, because you don't want to go down that hole of having millions of subclasses. On the other hand, there is a question of the repeating versus non-repeating. Other than that, we haven't got any clear subclasses, but I would say that there's some good work going into trying to understand that better. Now that we have, only recently did Chime actually publish 1,000 or so. So that's the data set to go looking after.
Okay, thank you, Keith. So we should move on. There are a few more questions in the Slack. So can I just remind speakers to please join the Slack so that you can answer the follow-up questions that have been asked. And can everyone join me again in congratulating Keith on the Anne Green Prize?